G'day, Year 10. So today what we're going to do is just work the last two examples from your notes and pretty much spend the whole double period getting you to play around with exponential functions, sketching them, and applying your knowledge to modeling questions. So let's get these last two questions done so you can get cracking with the work. So we've got a scenario where returning from camp, Sarah wanted a nice hot spa, lucky her, on the deck outside the family room. The water was still cold, so she turned on the thermostat to warm the water up to 22 degrees Celsius. And what we've got here is a situation where the temperature of the spa is modeled by this exponential function. So what I'm presuming with my limited understanding of thermodynamics is that when you heat water up, it doesn't go in a linear rate. What will happen is it will start to increase and then sort of kick like so. So it's modeled by an exponential function. All right, so let's use the table of values. So we're going to say 10 multiplied by 1.04 to the power of 0. Now that should be the initial temperature, which is 10 degrees. No wonder she wanted to heat it up. Okay, now after 5 minutes, 12.16, because it doesn't say rounding, I'm just going to dot it. I'm just going to change this to a 10. So that should be 14.80 degrees. So you can see here the temperature is gradually rising. 15 minutes, ooh, it's starting to get toasty. 18.009 ... 20, 21.911 ... and after 25 minutes, 26.65 ... Okay. Now what she's done is decided to warm the water up to 22 degrees, which is interesting because it, after 25 minutes, gets up to 25. All right, so let's see how this graph is going to work. All right, so the way I'm going to do this to graph it properly is to now, well, let's plot the first couple of points. Okay, so 0 is 10. And 5 is 12.6, 12.6, somewhere there. Right, and what I'm going to do is I'm going to work out how long before it gets to 22 degrees. So solve 22 equals 10 multiplied by 1.04 to the power of x, and can you solve for x? And this is basically asking the calculator for what value of time or x will you get to 22 degrees. And that's after 20.1 minutes. So let's sketch that in here. So this is roughly when it hits 22 degrees. And what I'm presuming happens after that is the temperature, or the thermostat, will make it remain constant. Okay, and now we're going to connect our exponential curve with this point here. Okay, now note that it's really hard to get a good curve here. So again, what we usually do on assessment is we just get rid of these grid squares here, which make it very difficult to sketch exponential functions. So I'm going to pretend that that point isn't there. Okay, so I know it says plot the points, but we won't get a nice smooth curve if we do, or the curve is going to look very much like a linear function. All right, so let's get it to curve up to that point there, and then it will stay at this point here. Okay, so the join happens at 20.10 ... comma 22 degrees. So it hits 22 degrees Celsius and stays that way, we presume, for as long as Sarah wants to stay in the spa. This key feature is when time is 0, the temperature is 10 degrees. So it increases exponentially to 22, then from 22 onwards it stays constant. Describe the way the water is changing. exponential growth until it reaches 22 degrees Celsius. So we've plotted it and answer the following questions to one decimal place. What's the initial temperature? We already know that. That's 10 degrees Celsius. Temperature after 2.5 minutes. Chuck that into your calculator. So we're going to go times 2.5. And it says to one decimal place. So 11.0 degrees Celsius. When did the temp reach 15? We can do that over here. 15 equals, so this tells us how long it takes before that happens. So it says to one decimal place, so we're going to adhere to the rounding. So that is 15, I'll just put my working out, equals 10 times 1.04 to the power of x. X equals 10.338 dot dot dot. Therefore, 10.3 mins. This one here, we should probably put our working out in, which is temperature equals 10 times 1.04 to the power of 2.5 equals 11.0. So that's the working out for that one. How long will Sarah have to wait before the temperature reaches 22? We've already answered that. That is going to be 20.1 mins. Right, so this question here on carbon dating, and again, if Ms. Downey or Mr. Kruger are listening to this, please don't go to town on my limited biology here, but carbon dating is a technique for discovering the age of an ancient object. So what I'm presuming is that you measure how much carbon-14 is in the thing that you've discovered, and they can tell that, oh, here it is. So while plants and animals are alive, their carbon-14 remains constant. So they'll have a certain amount of carbon-14 in them, but when they die, what will happen is the carbon-14 will decrease. And if they discover something, they can look at the amount of carbon-14 and work out how long it's actually been dead for. So the formula for it is this, where A counts as per minute per gram of carbon-14. So imagine you have two samples of wood. One was taken from a fresh tree and the other was taken from a charcoal sample found at Stonehenge and is 14,000 years old. How much carbon-14 does each sample contain? So for the first one, let's do the sample of wood, fresh tree. That's going to be A equals 15 times 0.9, so to the power of 0, because it's after 0 time, that is, it was just taken. So that's going to be 15, and it's measured in CPM per gram. Don't really know what that is, but that is the measurement, or how we, where is it? Counts per minute per gram, okay? Don't really need to know a lot about that, just need to know that it's got all of its carbon-14 still. Now, A equals 15 times 0.9 to the power of, and T, what's T? T is T thousands of years, okay? So this is going to be 14,000 years, so T is going to be to the 14. So jump on your calc for this one here, 15 multiplied by 0.9 to the 14. It's going to have 3.43 dot 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 CPM per G. How long does it take for the amount of carbon-14 in each sample to be halved? Okay, so for the first one, what we're going to do is say that A is equal to, the amount of carbon is equal to 7.5 equals 15 times 0.9 to the power of x. Okay, and what that will tell us when we solve for x is how long before the 15 grams of carbon end up at 7.5 grams of carbon. So again, we're going to jump into solve. 7.5 equals 15 multiplied by 0.9 to the power of x for x. And so we're going to say that x equals 6.57881 dot dot dot. And what does that mean? Well, remember x or t is in thousands of years, so we should be consistent with our variables here. That should be a t, not an x. T is there. So therefore, 6,579 years until that gets halved. Now, this one here, it's an interesting case here. So I'm going to do the next one. So this, when it was discovered, had 3.43. Okay. So what I'm going to do is grab that amount and halve it, which is 1.7. So we're going to say that for the sample of charcoal at Stonehenge, 1.715 dot 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 equals 3.43 dot 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 multiplied by 15 times 0.9 to the t. Now, this is going to sound a little bit crazy, but it should give us exactly the same answer as this because that's how long things take to halve. Okay, so it doesn't matter how much I actually start with, it should be the same to finish with. So to do this one on the calculator, just to sort of prove it to you, I'm just going to jump over here and go solve. And that's the amount equals the amount I started with, which is this amount of carbon-14 in the piece of charcoal, times 0.9 to the x for x, okay? And again, what I'm hoping for is that this should come up with 6,579, and it does, okay? So it takes exactly the same time to halve because, well, it's the amount of carbon and this is the half-life. So 6.5788 dot dot dot, therefore 6,579 years. Okay, charcoal from the famous, my French pronunciation is not that good, Lascaux cave in France gave a count of this. Estimate the date of formation of the charcoal and give a date to the paintings found in the cave. So we know that things start with 15, and this has ended up at 2.34. So if I go over and solve this, I get T equals 17.63373 dot dot dot. And because we're in thousands of years, 1, 2, 3, I'm expecting those paintings to have been done that many years ago. Okay, and I think if you Google that, I remember doing that in previous years, you'll find that that is roughly correct, I think. Okay, so what we then want you to do is do this table here. Now, it tells you to do it with all these values, but again, we're going to follow the same approach of just getting the endpoints. So 0 would have been 15, and after 17,000 years, so let's just get that one again. We've got 15 multiplied by 0.9 to the power of 17, which is 2.5. So it would be there, roughly. And what I would do if I was you is just try to connect that up with a nice smooth exponential curve. That's not bad. I'll take that one. I wouldn't plot the individual points. You'll find that, again, if you scales out, you'll get a jittery exponential curve. And I find students who do that, again, produce an exponential function that is like a connect the dots exercise. It sort of goes like this, then like this, then like this, then like this, then like this. to give you the world. I mean, I'm not saying my exponential functions are great, but obviously that's not really exponential. So if I was you guys, I'll just plot those endpoints in and just get a nice smooth curve that links them up. Okay. All right, so the questions will be posted on the Firefly page, so just check that with what you're expected to do. And as always, just ask us if you need any assistance.